Hey guys, welcome to 3.3 increasing and decreasing functions and the first derivative test. In this lesson we're going to be talking about the same thing we did in the last video, but with more emphasis on graphical representations and other kinds of functions that we don't deal with too much. So I want you guys to go ahead and quiz yourselves on this part here and this part. If you guys can just go ahead and just answer that without looking back to your notes, take 1 minute, and then we'll go ahead and discuss it in a few seconds. So put your video on pause. So number 1, we have if the derivative is greater than 0, then f is increasing on a to b. If the derivative is less than 0, then f is decreasing on a to b. And finally, if the derivative is 0, then we say that f is constant on a to b. The next part comes from your first derivative test, so that's if the derivative changes from positive to negative. It doesn't matter which one you did first. This one is a relative maximum. If the derivative goes from negative to positive, then this one is a relative minimum. So in the first example, we're going to be doing exactly the same thing as we did in the last video, in the last lesson, but this time we have a piecewise function. But the procedures for finding max and mins are still the same though. The process may be a little bit different since now we have a different kind of function. So the first things first is find the derivative. The derivative of a piecewise function is just the derivative of the top, which is 2, and the derivative of the bottom, which is 2x. Now, whenever you take the derivative of a piecewise, you lose equality, so it's not going to be x less than or equal to negative 1. It's going to be now x less than negative 1. You lose the equal sign, and the bottom one just remains the same since it didn't have an equal sign to begin with. And then the next step was to find critical numbers, and if you remember, critical numbers are defined as some c such that the derivative is 0 and some c such that the derivative is undefined. Well, if you notice, let's do the easy one first. If you notice, f of x is defined at negative 1, but is no longer defined at negative 1 for its derivative. So if it's not defined at negative 1, then that means that x is equal to 1 is undefined for the derivative, so that is a critical number already. The next part says, so that checks off the undefined part. Now let's go ahead and do the derivative equals to 0. We need to set this derivative equal to 0, but which one do we set equal to 0? We have to set the one that contains 0 in its domain. 2x is equal to 0. If you notice 0 right here, 2x is equal to 0, we need to plug 0. 0 belongs in this domain, so we need to plug it in there. So 2x is equal to 0, which means x is equal to 0 is our other critical number. Alright, so we have two critical numbers. Now let's go ahead and find increasing, decreasing intervals using the first derivative test. So this is from, let me draw that again. This is negative infinity, positive infinity, f prime f, and I have negative 1, 0. Those are my critical numbers. And then I want to go ahead and plug in numbers before it, so like negative 2, positive half, and 1. So I have three numbers to test in my derivative. So let's go ahead and plug them in. negative 2 belongs in which domain? This domain or this domain? Well, negative 2 has to be less than negative 1, so it's a top one. So if I plug in negative 2 here, well, there's no x to plug in, so my answer is simply just a constant 2, which is positive, which means that my derivative is increasing from here to here. Okay, so I'm sorry, I messed up with my my point here. This should be a negative half, not a positive half, because it's in between 0 and 1. So this should be, I don't know what I was doing, so this should be negative 1/2. Now if I plug in negative 1/2, negative 1/2 belongs in this domain. So I'm going to plug in negative 1/2 into my 2x. So 2 times a negative half, which is a negative 1, and that is less than 0. So that means that my derivative is negative, so it's decreasing from here to here. Finally, 1. If I plug in 1 into my same interval, 2 times 1, which is 2, and that is positive, so that means that it's positive here and here. Now, in the examples that we've been seeing, we've always seen alternating, increasing, decreasing intervals. I don't want you guys to assume that all functions are always alternating, increasing, and decreasing. There will be some functions, and especially in the AP exam, they want you to know your calculus. So there will be some functions at which where the decreasing or increasing will happen back to back. So I have a maximum. F has a max at x is equal to negative 1 because f prime changes from positive to negative. F has a minimum at x is equal to 0 because f prime changes from negative to positive. This is the kind of answer you need to provide when you're taking your AP exam for the free response part. If you don't have the rationale, then you probably will lose a point. Now, if you have your answer and your rationale, then that is probably 2 points. A lot of times they may be able to grade all that in 1 point. So even if you have your answer with no evidence to support, you may be losing out on the whole credit. F is increasing from, or let's say f is increasing on negative infinity to negative 1 and 1 to infinity because f prime is positive, and f is decreasing on negative 1 to 0 because f prime is negative. Now let's go ahead and check just to make sure our evidence is true. I have a graph that's going up and then down and then back up, so let's go ahead and graph this in my calculator, and there is a picture of my graph. Let me make that bigger. So it's true, f is going up to negative 1, and then after negative 1 it's going down to 0. I'm talking about x values here, and then after x equals 0 the graph goes up to increasing up again. So this graph definitely matched the evidence that we derived ourselves. So in the next video I'll go ahead and try to complete the rest of the problems in one video, so hopefully I'll see you guys there.